Welcome to Direct Current Deep Dive, exploring the technical framework of Current OS, a MOOC designed to dive into the principles behind Current OS technical decisions and their role in defining the electrical standard for DC microgrids. This video is part 4 of a 6-part series. Explore the remaining videos on the Current OS YouTube channel to continue learning about the world of direct current. In this video, we'll explain the underlying principles that drive Current OS's technical choices on electrical protection and the definition of risk categories. The aim is to deliver an arc-free solution that simplifies system design while reducing the need for cables and electrical equipment. Protection in DC systems marks a significant shift from AC practices. Why is this necessary? The primary reason lies in the fundamental differences between the electrical characteristics of AC and DC installations. On this slide, a basic installation with a bus and cables is represented, highlighting their inductance. In AC systems, the source is typically inductive, whether it's a medium to low voltage transformer or the alternator of a diesel generator. Similarly, many loads, such as motors or fluorescent tubes, are also inductive. In the event of a fault, such as a short circuit, these inductances result in current increases that are relatively slow, on the scale of tens of milliseconds. Electromechanical circuit breakers are well suited for this, reacting effectively within 10 to 50 milliseconds. In direct current, however, each source is capacitive, meaning that in the event of a fault, capacitors discharge rapidly. This includes the capacitors from sources and potentially from loads, depending on their characteristics. All these capacitors discharging simultaneously produce extremely high inrush currents within just a few microseconds. This rapid rise in current occurs too quickly for electromechanical circuit breakers to react. By the time they attempt to open, much of the capacitor energy has transferred into the inductance of the cables, and the breakers must then dissipate the stored energy in the cables. For a multi-source system like a building, this presents a major challenge. Calculating fault energy becomes highly complex, requiring detailed knowledge of every capacitor in the system. However, manufacturers rarely provide this information in their datasheets. Moreover, accurately determining cable lengths in a building is almost impossible. You would need precise layouts, and as buildings evolve, maintaining this information over time becomes impractical. To make things even more complicated, certain devices like batteries are sometimes loads and sometimes sources. The behavior during faults can vary significantly, especially with bidirectional systems, such as vehicles that supply energy back to the building, vehicle-to-building systems. As the number of sources and bidirectional systems increases, the complexity of calculating a protection plan for electromechanical circuit breakers in a DC microgrid grows exponentially. This is why a simplified approach is essential. Current OS addresses this challenge by categorizing circuits using the concept of zones. Zoning reduces complexity while ensuring effective protection for DC microgrids. What is the concept of zones? It's a method of mapping out an electrical schematic to classify areas based on their level of risk and protection. For example, let's consider a battery. At the battery terminals, the risk is extremely high. Any short circuit could cause catastrophic damage or even fire. This is classified as Zone 0, the most dangerous zone. To reduce the risk, a fuse is installed. Beyond this fuse, the area becomes Zone 1. The danger is significantly lower, but as mentioned earlier, currents can still be very high, and the risk of arc flash remains. DC does not naturally pass through 0, making it difficult to interrupt. Next, let's add a large converter. At its output, the converter has substantial capacitors that store a lot of energy, similar to a battery. As a result, the output of this converter is also classified as Zone 0. Adding another fuse reduces the risk again, returning this part of the circuit to Zone 1. On the same bus bar where the battery is connected, a converter linked to the public grid is also connected, which remains part of Zone 1. Now, an electronic circuit breaker can be installed. A new standard, IEC 60947-10, is currently being developed to define these electronic breakers. If the breaker trips in less than 10 microseconds, compared to traditional electromechanical breakers, which take tens of milliseconds, the area transitions to Zone 3. In Zone 3, Ultra-fast protections limit the contribution of different sources to a short circuit. Even the inductance of the cables ensures that only the closest source contributes significantly. This electronic protection effectively isolates the system from fault-related phenomena. The benefit is that designing a protection plan becomes much simpler. There is no longer a need to account for the integrated capacitors of various sources, the different line lengths, or the complex interactions between them. Instead, the installation can be calculated based on nominal conditions. Cables are sized for their nominal current, and protection planning becomes far more straightforward. With the introduction of electronic circuit breakers, most of the traditional protection calculations are eliminated. To summarize the concept of zones, as the zone number increases, the level of safety also increases. The safest zone is Zone 4. Why is Zone 4 safer than Zone 3? While both have ultra-fast electronic protections, Zone 3 is multi-source, meaning all sources must be deactivated to secure the circuit. In Zone 4, there is only one source, making it much simpler to identify and control the current source. This slide provides more detailed insights into the concept of zones through the official definitions presented in the System Reference Document made available to all current OS partners. This System Reference Document details the definition of each zone. In DC Zone 0, there is no electrical protection device, representing the highest level of risk. Any short circuit in this zone could result in catastrophic damage. Moving to DC Zone 1, protection is introduced through a fuse or circuit breaker with a response time of less than 50 milliseconds. However, significant arc flash risks remain, and system design becomes complicated. Calculating the behavior of every capacitor and cable length is essential but impractical for replication across projects. Design offices often rely on copy-paste methods for new buildings, reusing electrical layouts from previous projects. In Zone 1, this is challenging due to the variability of cable lengths and capacitor specifications, requiring a fresh design for each project. Additionally, topology presents issues, as all sources must connect to the main panel, adding more cables and complexity. In DC Zone 2.1, while the protections are classical, we operate behind converters that will limit fault currents. This makes it safer, but challenges remain. Sometimes fault currents are insufficient to trigger circuit breakers. Solutions include adding extra capacitors, which can revert the system to Zone 1 characteristics, or using external relays to activate breakers. However, the complexity of calculating protection plans limits the scalability and replicability of Zone 2.1 systems, making them suitable only for highly specialized designs requiring advanced engineering expertise. Zone 2.1 offers a notable improvement by reducing the risks of arc flash, which is a significant step forward. However, the system must limit the energy stored in capacitors with a maximum set at 600 joules. More details on this limitation can be found in the System Reference Document. This approach is supported by existing IEC standards and was previously used by ETSI in telecommunications. In DC Zone 2.2, hybrid circuit breakers are introduced. This is quite an attractive solution because the current doesn't flow through semiconductors all the time, so intuitively losses are reduced. This isn't necessarily true all the time, however, because inductances have to be added to protect these semiconductors, and there are often significant losses in the inductances. These breakers aim to reduce energy release during faults significantly, offering better safety than Zones 1 or 2.1. Compared with Zone 2.1, we've significantly limited capacitor discharge. Incident energy during faults has been further reduced. However, designing and implementing these systems still requires highly skilled engineers. Fault conditions must account for all sources, bidirectional devices, and converters, complicating calculations further. While Zone 2.2 allows for some degree of system replication and extensions, mastering transient phenomena and overvoltage issues remains critical. Standards groups are actively addressing these challenges, but full guidelines are not yet in place. Let's now look at Zone 3, the approach championed by current OS. Zone 3 takes the system further by utilizing fully electronic circuit breakers. These operate in just a few microseconds, typically under 10 microseconds, often closer to 1, 2, or 3 microseconds. This ultra-fast response drastically reduces incident energy during faults, addressing safety concerns that have traditionally made electricians wary of DC systems. Besides, fault-related calculations become unnecessary because faults are cleared so quickly that issues like cable overheating, electrodynamic forces, or contributions from distant sources are eliminated. They don't even have time to contribute. Fault energy no longer depends on the number of sources. Only the closest source contributes. It simplifies protection design and ensuring natural selectivity. The nearest breaker always trips first. Zone 3 also enables groundbreaking architectural changes in electrical distribution. Unlike traditional radial systems where all sources connect to the main panel, Zone 3 allows loop, mesh, or bus architectures. There's no longer any need to bring all the sources back to the main panel and start again with radial distribution. You can connect as close as possible to the bus. For example, photovoltaic converters on a parking lot are connected to the same point as the electric recharging stations underneath. Photovoltaic converters don't need to route through the main panel and then to EV chargers. This new architecture reduces copper usage significantly, cutting conductor requirements by 3 on a complete installation. There is no need to transferring energy from one point to another in a cable. DC can save conductors by changing the topology and organizing the cables differently in the building. This architectural innovation, paired with simplified calculations and enhanced safety, makes Zone 3 uniquely suited for commercial buildings, offering a transformative step forward from traditional AC systems. Current OS promotes Zone 3 because it brings new, unparalleled value to tertiary building and infrastructure. Zone 4 is the same as Zone 3 with a single source. Zones 3 and 4, championed by Current OS, introduce unique and groundbreaking benefits for commercial buildings, benefits that are distinctly different and entirely new compared to traditional AC systems. For personal safety in a multi-source system, several protective measures are implemented, including differential protections. However, in a system that is both extremely fast and multi-sourced, coordination becomes essential. This requires a mechanism to trigger all differential protections simultaneously or to cut off power sources collectively. To address this, Current OS promotes a solution called the inter-tripping wire. This is a simple yet highly effective method. Alongside the power cable, a small 48-volt wire runs in parallel within the same cable. This wire serves as a high-impedance signal. Yes, if it is short-circuited, the signal drops to zero without causing significant sparks. This high-impedance signal enables power conversion in the converters. When the signal drops to zero, the converters stop operating with a predefined response time. The inter-tripping wire is remarkably straightforward to implement and highly efficient, making it an essential feature in systems with multiple sources. Currently, in traditional setups, there is often only a single source, the public grid. Cutting all power simply involves tripping the main breaker. However, in tomorrow's multi-source buildings, power sources could be scattered throughout the structure. To intervene safely, it will be crucial to ensure that all power within a specific area is disconnected. The inter-tripping wire provides this assurance. Short-circuiting the wire to 0 volts in any location shuts down all sources in the surrounding zone. Importantly, this doesn't mean the entire building goes dark. Only the specified zone is isolated. This ensures that maintenance personnel can work safely, knowing the area is fully powered down. Additionally, the inter-tripping wire facilitates coordination among differential protections, ensuring seamless personal safety measures across the system. The inter-tripping wire not only enhances safety for workers, but also reinforces the overall reliability and efficiency of multi-source DC systems. Let's review the benefits and copper savings associated with Zone 3. Current OS promotes the claims that copper usage can be reduced by up to 2/3 in Zone 3 configurations. Understandably, this raises the question, how is that possible? First, let's start with a foundational concept. When transferring power through a DC cable, approximately 20% of copper can be saved compared to AC. This efficiency is due to the absence of the skin effect in DC, which allows better utilization of the cable's cross-section. This is why high-voltage DC HVDC, is used by utilities to transport energy over long distances. However, while this 20% savings is valuable, it alone isn't transformative enough for standard building applications. But Zone 3 allows us to achieve even more. The next point involves load voltage. Many modern loads designed for 230 volts AC internally convert that voltage to DC. For example, televisions, A-rated appliances like refrigerators and washing machines, and even computers all rectify AC to DC internally, typically operating around 350 volts DC. This means that the equivalent DC voltage for a 230-volt AC load is approximately 350 volts DC. We've already implemented setups where TVs and PCs are connected directly to 350 volts DC and they work seamlessly. By increasing the operating voltage, copper requirements are further reduced. The second factor is distribution topology. Consider this example. In a radial AC distribution system, if you have 10 loads, each requiring 10 amps, you need a 100 amp cable to supply them. However, in DC, thanks to components like diodes that prevent reverse energy flow, you can inject energy at both ends of the cable. This means that to support the same 10 loads, only a 50 amp cable is required. Additionally, unlike AC or Zone 1 setups, where all sources must route energy to a main panel before being distributed to loads, Zone 3's ultra-fast electronic protections allow energy to be injected or drawn from the bus at distributed points. So this distributed energy approach drastically reduces cable length. When comparing diagrams of AC and Zone 3 topologies, the reduction in cabling on the Zone 3 side is immediately apparent. You can see on the right-hand side of this slide two diagrams, AC, or Zone 1, and Zone 3. Zone 3 has less cables than AC, it is obvious. By combining all these factors, improved copper utilization, higher load operating voltages, distributed bus energy injection, and advanced topologies enabled by ultra-fast protections, Zone 3 achieves significant copper savings. In many cases, these savings reach up to 2/3. It's important to note that this is not a universal rule. The actual savings will vary depending on the specific building and project design. In some cases, the reduction may be less, while in others, it could exceed 2/3. However, across multiple projects, these observations consistently demonstrate the potential for substantial copper savings, making Zone 3 not only efficient, but a game changer for modern electrical installations. This concludes the electrical protection presentation of Current OS. Want to learn more? Check out the other 5 Current OS MOOC videos covering an introduction to Current OS, e-voltage bands, power management, pre-charging and earthing. Thank you for watching. See you in the next video.